ionic bond. So there are three types of bonds. There's ionic bond, metallic bonds, and covalent bonds, and that's the order we're going to do this in, so that we can master ionic bond before we move on, master metallic bond before we move on, and covalent bonds is like really long, and then we're ready for our unit test. Okay? And it's a long unit, so brace yourselves. So most of this beginning stuff should be kind of Science 10-esque. So atoms, except noble gases, are unstable. Why are they unstable? Because they have unpaired electrons. Is that the word you would have used, Xander?
Yeah.
No. Why are atoms unstable? Right. Normally we say full out. What you said is absolutely fine. They don't have a full outer shell, or they don't have a noble gas configuration. That's like the normal Science 10 token answer, right? Okay. So you know atoms aren't stable, but ions are. Why are ions stable? Because they have this elusive outer shell that is full. They have a noble gas configuration, okay? And therefore they're more stable than their atoms. So as you go along, you are annotating and highlighting and underlining with your note package to keep yourself engaged in the lesson. Because I've only done the bare bones, you need to add it so that it's personalized to you, okay? So these are Bohr diagrams. This should be quite familiar to you, where you have, I'm just going to see if I can move this a little closer because it's pretty difficult to see. Okay, all right. So potassium has, it's in period 1, 2, 3, 4, so therefore it should have 4 rings, right? 1, 2, 3, 4 rings with electrons in them. It's in group 1, therefore its outermost ring has 1 electron. Agreed? So 1 electron, and then you fill the rest. And that's what we were talking about last class, right? Or when I put those post-it notes on the board and we made our periodic table out of post-it notes. We were talking about how actually you don't really need to think about them. You don't even need to count them. I'm having a difficult time aligning this today. You just have to kind of look at the periodic table and it gives you all the hints. Potassium ion will have lost that 1 electron that's making it unstable, because we talked about how it could lose 1 or it could gain 7 in order to have a full shell. So it's going to do its easiest, which is to lose that 1. So there it is, gone. Right? Empty shells. That's the ion. 2, 8, 8, stop. That's Science 10, right? Here's your first new bit. The first new bit is that when I want to say an ion, I put these fancy square brackets and a positive charge, because this one's positively charged. Everybody okay? Make sense? Just one tiny little adjustment to be made. Okay, but by now, once you've passed Science 10 and passed it, I presume that you understand those inner rings are full. It's a little bit annoying to keep drawing them and keep filling them, and redundant, because you know it so well by now. And so we can just skip to what's called a Lewis diagram. This is our second new tidbit of information. Excuse me. So that potassium, which had 2 and 8 and 8 and 1, I'm now just going to draw that 1. Why? Because it's what makes it reactive and have the properties that it has. I cannot get this video today to work for me. Sorry, guys. It's doing that rainbow thing.
Junior class change.
Please? Pretty please? Chloe's just going to have to just deal with it. Okay, so K plus, 1 electron on the outside, or not K plus, K atom, 1 electron on the outside ring. I've made the inner rings disappear. But everybody understand they're still there. It's just a bit boring to talk about them because they don't actually do anything. They just sit there the whole time. Here's K plus, where it's lost the other electron. See, gone. The other rings are still there, but I'm just not drawing them. Square brackets, still, and a positive charge because this is 1 plus. Happy, everybody? Yeah.
Do you want us to put like the 1 plus, or does it just matter?
It doesn't matter to me. If you want to put 1 plus, you can. If it's 2 plus, you have to put a 2 there. But the 1 is personal choice. So we're not, this is how we write them from now on, are these ways. And not only is this called Lewis diagrams, this is a bit awkward. They're sometimes called electron dot diagrams, so they have two names. They're also called dot and cross diagrams, so that's three names. And then on top of that, they often have all the mixed up names. So not only are they called Lewis diagram or electron dot diagram, they're sometimes called Lewis dot diagram. They're sometimes just called the dot diagram. They're sometimes called the dot and cross diagram. Okay? So anything that has that kind of a name in it, anything with a dot or with Lewis, I mean these. Inner ring's gone, and I'm just talking about the outer ring. Okay? Okay. So here's chlorine atom. 1, 2, 3, 4, 5, 6, 7, because it's in group 7. The ones inside are full. Unstable because it doesn't have a full octet, a full valence shell, just like you already told me. Chloride, Cl minus, is a 1 minus charge because it's picked up an extra electron, and because it's in group 7, and everything in group 7 is 1 minus charge. So for any of those reasons that you fancy, I fill its shell because it's an ion. I put square brackets around it and it's a negative charge. Okay? Everybody okay with Lewis diagrams? All right. So here's two more new words. Lone pairs of electrons and bonding electrons. Now when I'm talking about these, I'm talking about only the valence electrons. Okay, so I don't really care about the inner rings that are full. I'm not talking about those, I'm talking about the outer electrons. And why is it called a pair of electrons? Why do we draw them like that? Well, you know in The Simpsons, and they have like on their nuclear reactor, they have this thing. Right? This is because actually in an orbit, in an atom, they have subshells in your outer shell. So this is all one outer shell. These are all the subshells in there. So look, here's an electron, here's an electron. They're a pair because they exist on the same suborbital, the same ring. Okay, they are both negatively charged, so they're at opposite ends of the ring, but as they move around the ring, they're on the same ring together. Okay, so there's one like that. These two are there. And that is a lone pair. See how they're paired on the same ring. Okay, so here's another one. Another lone pair. Here's another one. Another lone pair. And so chlorine has 2, 4, 6 I've drawn so far. And 7 because it's in group 7. So here's my 7th unpaired electron. Because it has nothing else on the ring. See that? So it wants to bond. It wants something to be added to it. So that is called a bonding electron. That one unpaired outermost electron. Does that make sense? Now, not really very often I won't give you, like, say, give me the definition of these. I might if it's multiple choice, and then you have to kind of find the right definition. But I'm more likely to say how many. So let's draw oxygen. Oxygen is in group 6. So how many valence electrons? 6. So 1, 2, 3, 4, 5, 6. You have to start drawing them like this. You can't, remember how I said to you in the last, like when we were just doing our revision, you could draw them anywhere you wanted. We have to start pairing them up now. So the rule is you go north, south, or pardon me, north, east, south, west, right? And then again, north, south, north, east, south, west, or whatever. Okay? However many you have. All right, so how many lone pairs does oxygen have? 2 lone pairs. Here they are. Put a circle around the lone pairs. How many lone pairs how many bonding electrons does oxygen have? to put a square around the bonding electrons. Do you get it? That's more the type of exercise I would have you do. Yes?
Why do those two, why do they not pair up, the two bonding ones?
Because, going back to this sort of diagram, if I have the first thing that's going to happen, I'll use a different color so I don't have to rub it out. The first thing that's going to happen is they're going to fill one in each circle because they repel each other. They're both negatives. So I'm more likely to go this guy going in this ring. That's the first electron. The second electron going in that ring, so it's all by itself. The third electron in that ring and the fourth electron in that ring. And that's what I mean by north, south, east, west.
Oh, yeah.
One in each ring.
Yeah, yeah. Okay.
And now, if I have a fifth, I guess I'm going to have to squeeze it in to here,
Yeah.
where I'm repelled. But if I stay at the other end, I'm just not repelled as much.
Okay.
Okay, so now I've got north, south, pardon me, I went 1, 2, 3, 4, and now I've got another one beside it. And then if I have another electron, I'm going to have to squeeze it into the, do you get it?
Yeah.
Okay? Okay. So that's how they fill in these suborbitals, and therefore that's how we fill them in our rough diagram of the suborbital. Okay? Okay. Any questions on that? Okay, so on the next page, I've got a little situation here. So I wish we had the apparatuses to make chlorine gas, and I'm ordering them, so we will one day. But if I had a jar of green chlorine gas, okay, so chlorine is naturally a green gas. It's green, you should know that because when you swim a lot, your hair turns green, right? And it's a gas at room temperature and pressure. So here's a jar of green gas, imagine. Taking some sodium. I'm warming it up. It's a metal. So like every other metal, well, like most other metals, it's silver, it's shiny, it's ductile, it's malleable, it conducts like every other metal. Okay? And I warm it up just to help the reaction go along, and I open up my lid to the jar of green gas, and I put my warm sodium inside the jar of green gas and shut it. Okay? The sodium is unstable because it's an atom, and it's not a noble gas. The chlorine is unstable because they're atoms, and they are not noble gases. So what would you predict would happen? Well, let's draw the Lewis dot diagrams to show what's going to happen. So the first thing I have is sodium and chlorine, and I'm going to do chlorine as an atom, not as a Cl2, just to make things really uber simple for us. Okay? So everybody okay with that? I'm ignoring that chlorine is a diatomic element for a minute. How would you draw the Lewis dot diagram for sodium? Xander. Good. Going to the periodic table. That's good. What group is it in?
1.
1. So how many valence electrons? 1. Dawson, what about chlorine? There's a periodic table on the side there.
7.
So how many valence electrons?
7.
1. I'm going to draw crosses here just to keep things a little bit in order for us. Okay, everybody okay with that? So 7, and can you see how I drew them in pair, pair, pair by itself? A, it makes it easier to count. 2, 4, 6, 8. 2, 4, 6, 7 in this case. And B, that's how they actually exist. Okay, so what happens? Unstable, unstable. What does sodium do to become more stable?
The bonding electron from the chlorine pair with the one from the sodium.
Okay, so it's got two options. One, it could pair and like share. Is that what you mean? What did you mean by pair?
Like
I was just watching
the
your
one from the
hands.
sodium and the one from the chlorine going together.
Okay, so I'm going to pretend you know what you mean. I'm not sure if you do. It's 50-50 as to whether you mean this. That this electron is going to leave sodium so that sodium's more happy, stable. Is that what you meant?
Yeah, I guess.
Okay. And it's going to transfer over to that empty spot in chlorine. So we call this a transfer. Okay, and what am I going to make? Well, what does the sodium become? Still Na, right? What's in its outer shell? 8 inside, but what did we do for the potassium? We left it empty. So empty, square brackets, and what charge does it become? Plus 1. What does the chlorine atom become? What's the chlorine atom become? -1. X, 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 like it had before. And a newly gained electron. And therefore it's overall negatively charged. Yes?
Do you have to like draw it as a dot there, or does it matter if you draw it as an X?
I'm drawing it as a dot to signify that this went here. And it makes it more obvious, because that's the story we're telling.
Yeah.
If I was just asking about chloride, there's no story to tell, so
Yeah.
you can do all 8 X's, or all 8 dots. And can you see why it's called a dot and cross diagram? Right? Dots and X's. And they say cross across the pond. They don't say X's. All right, so this put them together. Now you already kind of knew this in Science 10, only you never put square brackets, but you still would have said an Na plus and a Cl minus would come together and they make NaC, a table salt, or we scientifically call it sodium chloride, NaCl. Right, everybody? NaCl, sodium chloride. Nothing different, only now I've just sort of zoomed in to what the sodium looks like and zoomed in to what the chloride looks like and looked at the electrons in the outer ring. Do you have all of that written down? Okay. Okay. So why do we put them together?
They're both stable now.
They're both stable. Why don't they just, if they're that stable, why don't they just go and do their thing over there and go and do their thing over there?
Because they're bonded.
Why are they bonded?
Because they gave or took electrons.
No. What kind of bond are they, first of all?
Ionic.
Ionically bonded. They're ionically bonded because they're ions. Yes? Why would these two things stick together?
Because the chlorine has one of the sodium's electrons.
No.
Charges.
Bingo. What happens when you get something positive and something negative close together? They attract. Okay, so an ionic bond is an attraction of a cation and an anion. They're attracting. What happens when I get the north end of a magnet and a south end of a magnet close to each other? They stick together. Is that north end of the magnet stable? Could it be a magnet by itself? Kind of. I mean, it has the other end. But as soon as it gets close to another opposite charge, they stick together. Okay? So, stuck together is ionically bonded. They're ionically bonded because their attraction between the cation and anion. That attraction is scientifically called an electrostatic attraction. That's like the fancy way of saying positive and negative attract. An electrostatic attraction. So sometimes I use that word, electrostatic attraction. It's why the balloon that you've rubbed on your head sticks to the wall, an electrostatic attraction. Okay? Everybody get what an ionic bond is now. What do you think the octet rule is?
Have a stable octet, so it's stable, a full outer shell.
Good. Octet, oct means 8, the desire for it to get 8 electrons because then it's a full outer shell. Okay? So the octet rule is that all species want a full outer shell or want 8 electrons. Go ahead, write that down. I don't need to write it down for you. Species is just my way of saying thing. Atom, ion, particle. Okay? Not just my way, it's a chemist's way. So to have a full, or 8, outer electrons. Okay, for the video's sake, I'm just going to skip this bit, actually, now that I've just rotated it, and I'm going to go to this bit down here. Okay, one of the things that's really different about an ionic compound, and when we get going later, a molecular compound, is that when I say water, H2O, I really mean there are only 2 hydrogens and 1 oxygen connected together. Done. That's it. I don't mean potentially 4 and 2. I mean 2 and 1. The end. Game over. But when I say sodium chloride, Na+, and Cl-, so sodium chloride, I actually mean a 1-to-1 ratio. And that's why we don't go, Mg2 plus and O2 minus. Do we write Mg2O2? No. We write MgO. Okay? And what this means is there's a 1-to-1 ratio. For every 1 Na+, I have 1 Cl-. For every 1 Mg2+, I have 1 O2-. For every, in magnesium chloride, for every 1 Mg2+, I have MgCl2. For every 1 Mg2+, I have 2 Cl-. Okay, so I probably, in my structure of 1 grain of salt, have 100,000 magnesium 2 pluses. It'll be a lot more than that. Then I would have 200,000 chlorides. Okay? The reason is this. Let's do our magnets again. North pole, south pole attract. Everybody okay with that? Except for in my beaker, do I just have 2 magnets, a north pole and a south pole sticking together? No, I have a whole lot, right? 6 billion trillion if I have a mole of them. So if I have a whole lot of magnets in my beaker, isn't that north pole going to be attracted to a south pole magnet on my left, a south pole magnet on my right, a south pole above? Right? Correct? And the same thing happens with ions. This positive, or let's go with this negative ion here will be attracted to a positive above, a positive to the right, a positive to the left, a positive below, one behind and one in front. Okay, so it forms this, it's called a lattice structure, where I have like an alternation of charges as I go through. So I'm just going to show you some pictures of this. Here's sodium chloride, same big balls that I was just drawing on the board, but here you can see it a bit better, where you've got, you can see, pick one Na+ here, and can you see you've got a Cl- above, below, to the left, to the right, in front, and behind. Okay, and then pick a Cl-, you've got one above, below, right and left, in front, and you would have one behind, but we've chopped it off there so that we can see what we're doing. Does that make sense? And then a 2-to-1 ratio would give a different structure. So here's a 2-to-1 ratio. And you can see an Mg2+ for every 2 chlorides. And the chloride is surrounded by an Mg2+ as well. And I actually haven't gone and counted this. Oh, this is beryllium chloride. But beryllium is a 2+ charge as well, so it should be okay. I haven't gone and counted that to make sure I have exactly a 1-to-2 ratio to make sure this is 100% correct, this diagram, but you can see how it gives a different structure. And that's why different salts have different colors and different structures and different, because they have if you zoom in, their lattice structure is slightly different crystal. Does that make sense, you guys? Okay, so back to the package. And back to this sheet. And this is just Science 10 stuff. So I don't want you to do this whole thing, actually. because this is a Science 10 review. So I'm going to get you to do sodium 1 and 2, fluoride 5 and 6, 1 noble gas, and 1 that's a 2 charge. In fact, we'll stop there. Okay, so you're going to do 1, 2, 5, 6, 9, 11, and 12. And by the way, when it says structure, it's looking for how many electrons in the first ring? 2. How many electrons in the next ring? 8. Do you understand? Okay. And then on this side, I want you to do only 17, 18, 19, and 20, and we'll stop there. And that'll be this whole sheet, which is just Science 10 review, and then we're going to skip ahead and do the other sheet. Questions?